Hello everyone. I am Zhiyu, who will talk in this video about our recent work, SketchXAI, a first look at explainability of human sketches. Most previous explainable methods of images are to generate heat maps. And most explainable methods of text are to analyze the attention of different words. Considering explainability of sketch modeling, none of these explainable methods works well. In order to address this issue, we demonstrate a new methodology for explaining AI decisions on human sketch data. Instead of one static explanation per instance as in existing works, our proposed method supports generating infinitely many explanation paths with each dynamically showcasing the inner working of an AI classifier. This enables infinite varieties of explanation paths and allows humans to enjoy a wider coverage on how AI functions, and therefore better scrutinize AI. Sketches have various ways of representation. In a raster way, a sketch is represented as a set of pixels and we can use CNN models to process it. In a vector way, a sketch is represented as a list of points and we can use RNN, transformer or even GNN to process the vector. This is one of the reasons why the sketch is specific. It's like a combination of images and text. And we can always draw inspiration from the work in CV and NLP for sketch study, while for most sketch tasks we can learn a lot from other areas. Going back to explainability, it's quite the opposite. All advantages become disadvantages. Let's have a first look at explainability of CNN models. The most explainable methods of images are to generate heat maps. However, applying heat maps to sketches is a disaster. It's easy to explain the differences. For images, the explainable methods delete the redundant pixels and keep the pixels that have an impact on model prediction. While for sketches, usually, we can't find the redundant pixels. Let's move to NLP next. Most explainable methods of text are to analyze the attention of different words. While for sketches, we can replace the words with points. The attention maps look better than heat maps, but it still just meets the eyes. Neither the CV nor the NLP explainable methods work well for sketches. No worries, let's analyze step by step. At first, I will introduce a concept, interpretable components. What is the interpretable component? Most explainable methods usually provide a qualitative understanding of the relationship between the instance's components and the model's prediction. For images, the interpretable components are pixels, superpixels or patches, but human cannot understand these components very well. In the end, it is semantics that are understood and accepted by human. For text, the interpretable components are words. As language is created by humans, it is naturally understood by humans. Now considering sketches. Shall we explain sketch models by pixels or points? Either pixels or points are the way machines record sketches, not the way human understands sketches. If you tell someone who is not familiar with sketch that a sketch contains 100 points, he or she must think you are mad. Then shall we build semantics for sketch? As sketch is a highly abstracted form of human vision, sketch semantic itself is an extremely difficult problem to define. So what can we do? We think strokes may help us. Because strokes are natural components of sketches and are easily understood by human, we build a stroke-based framework called SketchXAI. All previous sketch classifiers, no matter whether CNN-based or RNN-based, all take sketch as a whole. They make calculations between all pixels or points. In fact, when we draw a sketch, we only make calculations within each stroke to control the shapes of strokes. Since the starting point of each stroke determines the location of the stroke, human also do other kinds of calculations to determine the locations of different shapes. Put the right shape in the right location. That's the process of human sketching. In addition, we think order is also an important attribute. It may have less impact on classification accuracy, but it reflects the human thought process. We analyze the three attributes of strokes and construct a new framework based on them. We set the starting point of each stroke to be the center of the canvas and use that as its shape, using the real coordinate of the starting point as the location. And then we can build the shape embeddings, location embeddings, and order embeddings respectively. Finally, we add up all embeddings as input to the standard transformer encoder with the cross-center AP loss function. There is always a trade-off between the performance and explainability of deep models. We can't only focus on explainability with a poor performance just like using a white box. From the table, you can see we beat the state-of-the-art with the smallest parameters. Here is a comparison between positional embeddings in Vision Transformer and order embeddings in our model. As you can see in this similarity map, the earlier strokes are independent of each other and the further you go the more similar the order embeddings become. Our order embeddings show the distribution of the number of strokes in all sketches. Over 90% of sketches have no more than 10 strokes. As order embedding is a learnable dictionary, it is difficult to get an effective gradient for the order index over 10. Here is the visualization of shape embeddings. I make k-means clustering of all stroke embeddings and use TSNE to visualize the strokes in the clustering centers. We can see our sketch classifier creates a good stroke shape embedding space. And we can apply this to some downstream tasks like sketch reconstruction. Here is a qualitative evaluation between our shape replacement and primitives. You can see natural strokes work better than handmade prompts. Our most important contribution is the proposal of an explainability task dedicated to sketches, SLI. To make it easier to understand, I'll explain it through the figure. After training the model, we have a good classifier. Then we freeze the model and set the location input as learnable parameters. Therefore, when I set a label and make a backpropagation, the gradient will be added to the location of different strokes through the red path. We design two settings, recovery and transfer. Recovery means setting locations all to 0 and the label to the original category, to see if our model can recover the sketch. Transfer means setting the label to another category, and to see if our model can reorganize the strokes. Let's see some interesting explanations. All original samples are selected from test set of Quick Draw. The model never saw these samples during the training stage. And the input column means I delete the location information so strokes will be put in the center of the canvas. I set the max optimization iteration is 100. The number in the top left corner means the probability that the model considers it to be the original category. The category in the bottom left corner indicates the label given to the current sample by the model. Since this model cannot make shape transformations, it is often easy to complete attacks between categories with similar shapes of strokes. For example, you can't ask a book to become a bicycle, because there's no curve in the book sample. But with a strong cherry pick, we can find some more interesting examples. The number in the top left corner means the probability that the model considers it to be the original category. The number in the bottom left corner means the probability that the model considers it to be the new target category. It is worth noting that in the training process, we do not set the restriction that the strokes must be within the canvas. In the transfer process, the model will throw unwanted strokes out of the canvas. For example, in the last example, the model does not consider this stroke representing the car body will be helpful in classifying the bicycle, so it is gradually moved to the bottom of the canvas. It is often said that there is a trade-off between model performance and explainability. In my opinion, I find there is also a symmetry between them. Compared to general training, the inversion explanation is to exchange the roles of model and data. The general classification is that we give a question to the classifier, what label matches the sample? In contrast, the explanation process is another question to the classifier, what sample matches the label? The code is also very simple. Keep the original pipeline and just change 2 lines, set your data into a learnable parameter and freeze your model. I hope you can also notice the beauty of this symmetry. In the end, let's watch the whole dynamic process of the SLI explanation. We believe that this work will make people aware of the differences between sketches and other modalities and the differences in the explainable methods they apply. And the greater hope is to stir up the community and motivate follow-up works in this new direction of human-centered data for XAI. Please visit our project page for more details. We will present our work at CVPR 2023 on Thursday afternoon with poster number 260.